Every atom in your body should have collapsed long ago. The electrons circling the nucleus should spiral inward, crash, and take all matter down with it. Every physicist before 1900 knew this. Every equation said the same thing. Matter had no right to exist. And somehow, here you are. Today we go inside the atom. We follow an electron to the edge of its world, watch it reach the nucleus, and find out why it refuses to fall in. If you enjoy the journey, subscribe and stay with us. Prepare yourselves. We begin. Picture the last solid thing you touched today. A desk, a phone, a wall. Whatever it was, it felt real, permanent, built to last. Now imagine a group of some of the smartest people who ever lived, sitting around in the early 1900s, staring at their equations, and coming to one terrifying conclusion. Every single one of those solid things should have already stopped existing. Every atom, every molecule, every grain of dust on this planet. Gone. Collapsed. Over. This was not a small worry at the edge of physics. It was the central crisis of an entire era of science. And the strangest part, their math was correct. If you followed the laws of physics as they were understood at the time, matter had no reason to exist. The atom was supposed to destroy itself almost instantly after forming. The electrons circling the nucleus should have radiated away all its energy, spiraled inward like a dying satellite, and crashed into the center in less than a fraction of a second. Physicists called it the collapse problem, and it meant that by all rights, the universe should be a featureless soup of collapsed particles instead of stars, planets, and you sitting here right now. So why does matter exist? That question took the greatest minds of the 20th century decades to answer, and the answer, when it finally came, broke physics open in ways nobody expected. It rewrote what energy means. It rewrote what location means. It rewrote what an electron actually is. But before we get to the answer, we have to understand the problem, because the collapse problem only makes sense if you understand the model of the atom that predicted it. In the early 1900s, most scientists pictured the atom like a tiny solar system, a heavy nucleus sitting at the center, and one or more electrons flying around it in circular paths, the same way planets orbit the sun. It was a clean picture, satisfying, easy to draw on a chalkboard. The problem was what happened the moment you applied the known laws of electricity to that picture. An electron is a charged particle. When a charged particle moves in a curved path, it accelerates, and when a charged particle accelerates, it releases energy in the form of radiation. This was not a guess. This was one of the most tested rules in all of physics. Every radio tower on Earth works because of exactly this principle. So the electron, curving around the nucleus, should constantly be bleeding energy away, a little bit lost every single loop. And as it loses energy, its orbit gets smaller. It spirals inward, faster and faster, tighter and tighter, until it hits the nucleus. Scientists calculated how long that spiral would take. The answer they got was about 16 trillionths of a second. That is how long the atom had before it should destroy itself. Every atom, instantly, before anything could form, before life, before chemistry, before a single molecule of anything. And yet matter clearly exists. The chair is still there. You are still here. Something in those equations had to be wrong, or something about the electron had to be fundamentally different from what anyone imagined. What came next would shatter the entire picture of the physical world, starting with an experiment so strange its results seemed like a mistake. In 1911, a physicist named Ernest Rutherford stood in front of a blackboard and drew a picture that changed science forever. He sketched a tiny dot at the center, surrounded by small circles flying around it in neat orbits. It looked exactly like a miniature solar system. Electrons were the planets, the nucleus was the sun. Rutherford had just finished one of the most famous experiments in the history of physics. and that experiment had forced him to this picture. His data showed clearly that the atom had a dense, heavy center and a huge amount of empty space around it. So the solar system model felt like the only thing that made sense. His student, Niels Bohr, took that picture and ran with it. In 1913, Bohr published a model where electrons traveled in fixed circular orbits at specific distances from the nucleus, like lanes on a highway. Each lane had a specific energy. An electron could jump from one lane to another, but it had to stay in a lane. This model worked shockingly well for hydrogen. It predicted the colors of light that hydrogen emits when heated, and those predictions matched real measurements almost perfectly. Scientists were excited. It felt like the atom had finally been cracked. But buried inside the model was a disaster waiting to surface. The Bohr model borrowed a rule from classical physics. Electrons move in circular paths, and circular motion means the electron is always accelerating, always changing direction. And according to Maxwell's equations, the foundation of all electricity and magnetism, any accelerating charged particle must continuously emit electromagnetic radiation. So the electron should be radiating energy away the entire time it orbits. Every single loop, every fraction of a second, the orbit should shrink and shrink. Physicists worked out the timescale. For a hydrogen atom, a classical electron would spiral all the way into the nucleus in roughly 16 trillionths of a second. That number is so small, it almost has no meaning. It is shorter than the time it takes light to cross a single human hair. Bohr knew about this problem. His solution was simple, which is another way of saying it was unsatisfying. He just declared that electrons in allowed orbits do not radiate. He said it was a rule. He offered no deeper explanation. You could follow the rules of his model and get correct predictions, but if you asked why those rules were true, he had no answer. That kind of answer makes physicists uncomfortable. Rules without reasons are just observations dressed up as explanations. The deeper problem was that Bohr's model gave up on explaining why the electron does not crash. It just commanded the electron not to. It posted a no-collapse sign at the lowest orbit and called it done. For about a decade, that was enough. The predictions were too good to ignore. Bohr won the Nobel Prize in 1922. His picture of the atom appeared in textbooks everywhere. But the no-crash rule had no foundation. It was a wall built from nothing, and physicists knew that sooner or later someone would have to explain what that wall was actually made of. That explanation, when it came, would require throwing out the very idea that an electron has a fixed location at all. Something strange was about to replace the planet in its orbit, something that could be everywhere and nowhere at the same time. The year was 1909. Ernest Rutherford handed two of his students, Hans Geiger and Ernest Marsden, a task that seemed almost too simple. They were going to fire tiny particles at a sheet of gold foil, thinner than a human hair, and see what happened on the other side. The particles they used were called alpha particles, small bundles of matter carrying a positive electric charge fired from a radioactive source. The detector on the other side was a screen coated in zinc sulfide, a material that would flash whenever a particle hit it. The experiment was supposed to confirm the existing model of the atom. At the time, scientists believed the atom looked like a pudding, a soft, spread-out blob of positive charge with tiny electrons embedded inside it, like raisins stuck in a muffin. In that model, the positive charge was so spread out and so weak that the alpha particles should sail straight through the foil, barely deflected at all. And for most of the particles, that is exactly what happened. They went through. They barely moved. Confirmed. But some of them bounced back. Not deflected slightly. Bounced. Straight back toward the source, as if they had hit a wall. Rutherford later said, "It was as if you fired artillery shells at tissue paper and they came back and hit you." He was not exaggerating. That is exactly how impossible it seemed. The only explanation that fit was radical. The positive charge in the atom had to be concentrated in an incredibly tiny, incredibly dense region at the center, a region so small compared to the overall atom that almost every particle flew through the surrounding space without touching anything at all. Rutherford did the math. The nucleus had to be roughly 100,000 times smaller than the whole atom. Imagine the atom the size of a football stadium. The nucleus would be a marble sitting on the 50-yard line. Everything else, all the space where the electrons live, would be empty. Completely empty. The atom was more space than matter. Almost entirely hollow, every solid thing in the world was, at its foundation, nearly nothing. That was shocking enough on its own. But it created an immediate problem. If the nucleus is that small and that dense, and if electrons orbit around it in circular paths, then the atom is an accelerating charge system, and accelerating charges radiate, and the energy bleeds away, and the electron spirals in. The empty space gave the electron plenty of room to spiral through before hitting the nucleus, and the calculation said it would use every bit of that room in 16 trillionths of a second. The experiment that proved the atom was mostly empty space was the same experiment that made the atom's survival seem impossible. Rutherford had built a beautiful trap. He proved the atom existed in a form that should not be able to exist. For the next 2 decades, physicists chased this contradiction. They knew the solar system model had to be wrong in some deep way. They just could not agree on what was wrong, or what to replace it with. The answer would eventually come from a direction nobody expected. It came from asking a question so basic that most people never thought to ask it. What is an electron, actually? And the answer to that question was about to destroy every picture anyone had ever drawn. Atoms are mostly empty. You have probably heard that before. But hearing it and actually feeling what it means are 2 completely different things. So let us make it real. Imagine taking a single hydrogen atom and blowing it up to the size of a professional football stadium. The whole thing, end zones, upper deck, parking lot, everything. That is the full atom. Inside that enormous space, where is the nucleus? Sitting at the 50-yard line, about the size of a marble, one marble, in the middle of a football stadium. That is the ratio of nucleus to atom. And the electron is somewhere out in the stands, buzzing around. But here is the part that makes this hard to picture. There are no seats the electron is required to sit in. There are no walls, just the electron, the marble at the center, and an ocean of nothing between them. If you scaled yourself down to the size of an atom and stood inside it, you would see almost nothing. The space would be vast, dark. You would have to travel an enormous distance before reaching anything solid at all. And yet, solid objects feel solid. You can press your hand against a wall and it pushes back. A steel floor holds your weight. A glass window stops the wind. How can something be almost entirely empty and still feel completely solid? That question has a real answer, and we will get to it deeper into this story. But for now, the emptiness itself matters because it is what creates the collapse problem. All that empty space is the room where the electron should be spiraling down. 16 trillionths of a second, according to classical physics. That sounds fast, because it is. Nothing about that empty space should protect the electron. In the classical picture, it just gives the electron more room to lose before hitting the nucleus. Here is something even stranger, though. The atom being mostly empty is not the weird part. The weird part is that the electron is supposed to be somewhere in all that empty space, at a specific location, moving in a specific direction, like a tiny planet. And that specific location, that specific direction, those things do not exist. The electron does not have them. When you try to pin down where an electron is at any given moment, the universe refuses to cooperate. The electron is smeared out across the entire space. It occupies all of it at once. In a probabilistic way, it is not hiding somewhere, and you just cannot find it. It genuinely does not have a single position. This is the part where the old model completely breaks down. You cannot spiral into the nucleus if you do not have a path. You cannot lose energy orbit by orbit if you do not have an orbit. The electron is not a marble rolling around a bowl. It is something far stranger, something that behaves more like a wave than a particle, something whose very nature prevents the collapse that seemed mathematically inevitable. But understanding that requires understanding what a wave actually does when you try to squeeze it. And the answer to that question came from a man who was only 25 years old, sitting in a small room in Munich, trying to solve a problem he thought was simple. Let us slow this down and make it vivid, because the collapse scenario is not just a prediction on paper, it is a physical process with a clear mechanical story, and once you see it step by step, the impossibility of matter's survival becomes almost unbearable. Start with the electron in its orbit. It is moving, curving, chasing the nucleus around and around in a tight loop. Now the electron carries an electric charge. That charge is fundamental. You cannot turn it off. And here is the rule that causes all the trouble. Any charged particle that accelerates, meaning any charged particle that changes speed or direction, produces electromagnetic radiation. Electromagnetic radiation is the same thing as light, radio waves, microwaves, X-rays. They are all the same kind of energy, just at different frequencies. When a charged particle accelerates, it launches that energy outward. As a wave, it radiates. A radio tower works exactly this way. Electrons in the tower's antenna are pushed back and forth, accelerating constantly. That motion launches radio waves outward at the speed of light. Your car radio picks them up miles away. The physics is identical. Now put that same physics inside an atom. The electron curves around the nucleus. Every single time it changes direction, which is every fraction of every second, it should launch a tiny burst of electromagnetic radiation outward, a tiny pulse of light escaping into space. But that energy has to come from somewhere. Energy is conserved. The radiation carries energy away from the system, and the only energy available is the electron's own kinetic energy, the energy of its motion. So the electron slows slightly. A slower electron cannot maintain the same orbit. Gravity pulls a slower planet into a closer orbit, and the same logic applies here with electric force. The electron drops closer to the nucleus. Closer means it moves faster to maintain the orbit. Moving faster means curving harder. Curving harder means radiating more. More radiation means more energy lost, which means a tighter orbit, which means faster motion, which means even more radiation. It is a feedback loop with no off switch. Each step makes the next step worse. The electron spirals inward at an accelerating rate. Scientists calculated the total time from start to finish, from the electron at a normal orbital distance, all the way down to the nucleus. The answer was about 16 trillionths of a second, less than the time it takes light to cross a single human hair. The atom would not slowly decay, it would collapse so fast the word instant barely covers it. And here is why this mattered beyond just electrons and nuclei. If atoms collapse, chemistry collapses with them. No stable atoms means no molecules. No molecules means no water, no air, no cells, no planets, no anything. The universe, if classical physics were the whole story, should be a cold, featureless cloud of collapsed elementary particles. The fact that you are listening to this is proof that something is wrong with that picture. Something deep in the structure of the physical world refuses to let the spiral happen. But finding out what that something was required, scientists to question the most basic assumption of all, the idea that a particle has a definite location and a definite path in the first place, and questioning that assumption led somewhere nobody was ready to go. By 1913, the crisis was clear. Classical physics predicted atomic collapse. Matter should not exist, and yet atoms were everywhere, stable, holding together without any sign of trouble. Something was wrong, and the pressure on physicists was enormous. Niels Bohr, a young Danish physicist working in Rutherford's lab, decided to do something radical. He decided to stop asking why and start asking what if. What if electrons were simply not allowed to radiate while in certain orbits? What if some orbits were special, stable by decree, immune to the collapse problem? What if the electron could only exist at certain fixed distances from the nucleus and nowhere in between? Bohr had no physical reason for any of this, no deeper theory, no mechanism. He was essentially writing new rules for electrons out of thin air. But he had a powerful test waiting for him: the spectrum of hydrogen. When you heat hydrogen gas, it glows, and the light it emits is not a smooth rainbow. It comes in specific, sharp colors, distinct lines: red, blue-green, violet. Scientists had mapped those lines precisely for decades and had no explanation for why they existed. Why those exact colors? Why not a continuous glow? Bohr's new rules predicted exactly those colors. When an electron jumps from a higher allowed orbit to a lower one, it releases a packet of light whose energy matches the gap between the orbits. Different gaps, different colors. His calculations matched the measured lines almost perfectly. Hydrogen's spectrum was Bohr's proof. The rules worked. The atom had a lowest orbit, a ground state, and the electron could not fall below it. Below the ground state was simply nowhere to go. But there was a massive problem hiding inside the success. Bohr's model worked for hydrogen: one electron, one nucleus. When scientists tried to apply the same rules to helium, the next simplest atom with just 2 electrons, the predictions fell apart. The model was not a true description of atomic structure. It was a recipe that happened to work for the simplest case. And the deeper problem remained. Bohr had banned the collapse by command, not by explanation. He said electrons in allowed orbits do not radiate. But why? What stops them? What is special about those orbits? He had no answer. Physicists knew that Bohr's model was a stepping stone, not a destination. It had captured something real about atoms. The allowed energy levels were genuinely real, but the picture of circular orbits was almost certainly wrong. Electrons did not behave like planets. Something else was going on. In the years that followed, a small group of physicists began attacking the deeper question. They were looking for a theory that would explain why certain energy levels are stable, not just declare them so. They wanted to know what the electron actually was, what it was actually doing when it was not jumping between levels. The answer required a completely new kind of physics, and it came partly from a strange observation. Light, which everyone had always assumed was a wave, sometimes behaved exactly like a particle. And matter, which everyone had always assumed was made of particles, sometimes behaved exactly like a wave. If an electron was a wave, the entire collapse problem might dissolve on its own. But getting there required a discovery so strange that even its creator could barely believe it. In the summer of 1925, Werner Heisenberg was 23 years old and suffering from a severe hay fever attack. He left Göttingen, Germany, and travelled to a small rocky island called Helgoland in the North Sea to recover. Away from the pollen, alone with his equations, he began writing down a completely new way of describing how electrons behave. He was not trying to find what electrons look like. He gave up on that entirely. He focused only on what can be measured: energy levels, light emitted, frequencies, things you can actually detect with instruments. What emerged from his weeks on that island was the beginning of quantum mechanics, a set of rules for predicting atomic behavior that had almost nothing in common with classical physics. It was abstract, it was mathematical, and it led 2 years later to the most famous and most misunderstood principle in all of science: the uncertainty principle. Here is what it actually says. There are pairs of properties in nature that cannot both be known precisely at the same time. Position and momentum are one such pair. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and the more precisely you know its speed and direction, the less you can know its position. This sounds like a measurement problem, like you are just bumping the electron around when you try to look at it. But that is not what it means. The uncertainty is baked into reality itself. The electron does not have a precise position and a precise momentum at the same time. Those quantities are genuinely undefined until measured, and measuring one disturbs the other. Imagine you are trying to pinch a cloud. The harder you squeeze, the more it puffs out in other directions. You cannot compress it into a single point, because the act of compressing it causes it to spread out in other ways. The electron behaves similarly, except the spreading out happens in momentum space rather than physical space. Here is why this kills the collapse problem. For the electron to crash into the nucleus, it would have to be located exactly at the nucleus, a single precise point in space. But if the electron's position became that precise, its momentum would become completely uncertain, meaning it could be flying in any direction with any speed. The average momentum uncertainty would be enormous. Enormous momentum means enormous kinetic energy. Enormous kinetic energy means the electron would instantly fly away from the nucleus rather than stay there. The very act of confining the electron to a tiny space generates a powerful energy that pushes back. Squeeze harder, and the pushback grows stronger. There is no amount of squeezing that collapses the electron into the nucleus, because every attempt to define its position more precisely generates more energy that fights the confinement. This is the real reason atoms do not collapse. The electron cannot reach the nucleus because reaching the nucleus would require a position precision that nature forbids, and the price of that precision is an explosion of energy that flings the electron away. Heisenberg had not just solved the collapse problem, he had revealed something about the nature of reality itself. Position and momentum, two things that seem simple and obvious, turn out to be fundamentally linked in a way that changes what it means for a particle to exist. And once you accept that, the atom changes its shape completely. The uncertainty principle sounds like a limitation, a wall you hit when your measurements get too precise, but it functions more like a physical force, one that gets stronger the more you push against it. Think of it this way. Imagine you have a spring trapped inside a box. You press the lid down, the spring compresses. The more you push, the harder it pushes back. At some point, the spring's resistance balances your push, and the lid stays at a fixed height. You cannot press it all the way flat, without infinite force. The electron inside an atom behaves almost exactly like that spring. The atom is the box. Squeezing the box means confining the electron to a smaller region of space, and the uncertainty principle is the spring. Here is the physics in plain terms. When you confine a particle to a smaller region, its position becomes more precisely defined. Heisenberg's principle says that when position gets precise, momentum gets uncertain. Uncertain momentum means the electron could be moving in any direction, with a wide range of speeds. When you average out all those possible momenta, you get a large typical momentum. Large momentum means large kinetic energy, and large kinetic energy means the electron is moving fast and energetically, fighting to escape whatever is confining it. So confinement raises energy every time. Squeeze the electron's allowed space by half, and the energy it needs climbs sharply. This is a real, measurable, calculated effect. It is not a metaphor. Now apply this to the atom. The electron orbits at a certain distance from the nucleus. If you tried to push it closer, you would be confining it to a smaller region. The uncertainty principle would immediately respond by generating more kinetic energy. That kinetic energy fights the confinement. The electron resists being squeezed. At the ground state, something exact happens. The distance where the electric attraction pulling the electron inward is perfectly balanced by the quantum energy pushing the electron outward. These two forces arrive at a standoff. The atom settles at that balance point and stays there. Push the electron closer and the quantum energy wins, pushing it back out. Let it drift farther and the electric force wins, pulling it back in. The ground state is a stable equilibrium, a resting point with no bottom below it. This is why the atom does not spiral inward. It is not that something physically blocks the electron at a wall. It is that moving closer would cost more energy than the atom can access. The system finds its lowest energy configuration and stays there, locked in place by the balance between attraction and quantum pressure. There is something almost beautiful about this. If you sit with it for a moment, the universe found a way to make matter stable. It encoded a resistance to confinement directly into the fabric of reality. Without the uncertainty principle, every atom in the universe collapses. With it, every atom in the universe holds. Every solid surface you have ever touched exists because of that invisible spring. And if you think that is the end of the story, the next part is going to change how you see the electron entirely. Because the electron is not actually a tiny particle bouncing around in a box. It is something far stranger, something that was hiding in plain sight since the moment scientists first measured it. Here is the question that broke the atom open. If you fire a single electron at a barrier with two small slits in it, where does the electron land on the other side? The answer should be simple. A particle goes through one slit or the other. It hits the detector in one spot. That is what particles do, but that is not what electrons do. A single electron fired one at a time produces an interference pattern on the detector. Stripes, bright bands, and dark bands, like ripples crossing each other on a pond. The pattern that only appears when a wave passes through both slits simultaneously and interferes with itself. A single electron, no partner, nothing else in the experiment. And it behaves like a wave that passed through both slits at once. This experiment has been done hundreds of times with increasing precision. It is one of the most confirmed results in all of physics. The electron is not a tiny ball. It has wave properties that are real and measurable, and those wave properties determine where it can and cannot be found. What does it mean for an electron to be a wave? It means the electron does not have a single location. It has an amplitude at every point in space, a number that tells you how strongly the electron's presence is felt at that point. Square that amplitude, and you get a probability how likely you are to find the electron there if you measure. Before you measure, the electron is genuinely spread out. Every point in space has some probability. The electron is a smear, a cloud, a blurred presence extended through a region of space. Physicists call this a wave function. The wave function of an electron in an atom wraps around the nucleus in a specific shape depending on the electron's energy. At the lowest energy, the ground state, the wave function forms a spherical cloud centered on the nucleus, dense near the center, fading at the edges. No sharp boundary, no fixed orbit, just a probability cloud that tells you where the electron is likely to be. This changes everything about the collapse problem. You cannot spiral something that has no path. You cannot ask how close the electron gets, the way you would ask how close a ball gets, because the electron is already everywhere in its cloud simultaneously. There is no single electron at a specific distance that's slowly decreasing. The electron's wave function has some amplitude even right at the nucleus. Right at the center, the electron is already overlapping the nucleus in a real measurable way, and the atom is still completely stable. That sounds paradoxical. If the electron reaches the nucleus, should the atom not collapse? The answer is no, and understanding why requires understanding the difference between reaching and crashing, between overlap and collision. But first, there is one more piece. The wave function has a specific shape at the lowest energy level, and that shape tells you something precise about where the electron spends most of its time. The answer is surprising. The place where the electron is most likely to be is not the center, even though the wave function is technically strongest there. The reason why requires a small trick of geometry, and once you see it, the atom becomes much clearer. Every building has a ground floor. Below it, the sidewalk. Below that, the foundation. You can keep digging, but you cannot float below the ground. The electron in an atom has a ground floor too. Physicists call it the ground state. And below the ground state, there is nothing. No lower level, no next step down. The electron cannot fall any further because further does not exist. This sounds like a rule someone made up. In the Bohr model it was. Bohr declared a lowest orbit and told the electron to stay there. But in quantum mechanics, the ground state is not a declaration. It is a consequence, a mathematical result that comes out of the wave equation automatically. Here is how to think about it. Electrons in atoms exist in specific wave patterns, the same way a guitar string can only vibrate at specific frequencies. A guitar string stretched between two fixed points can vibrate in a smooth single arch, or in two arches separated by a still point in the middle, or three arches, or four, but it cannot vibrate in half an arch. The wave has to fit the boundary conditions. Fractional waves do not work. The electron's wave function around the nucleus has the same kind of constraint. The wave has to close on itself smoothly. It has to be stable. It cannot just be any shape. Only certain shapes are allowed, and each allowed shape corresponds to a specific energy level. The simplest shape, the lowest energy shape, is a smooth sphere centered on the nucleus. No extra waves, no internal loops, just the simplest possible cloud. That is the ground state. To go to a lower energy state, you would need a wave shape simpler than a sphere. But there is no simpler closed three-dimensional wave. The sphere is already the minimum. The ground state is genuinely the bottom of the staircase. And below it, there are no stairs. This is the mechanical reason the atom does not collapse. The electron does not fall below the ground state, because the wave equation has no solution for anything lower. Ask the universe for an atomic state with less energy than the ground state, and the math itself says no such thing exists. Now here is the part that catches people off guard. Physicists have measured how close the electron gets to the nucleus in the ground state. The answer is that the electron's wave function extends all the way to the nucleus. The probability of finding the electron right at the center of the nucleus is not zero. There is a small but real amplitude there. So the electron is, in a real mathematical sense, sometimes at the nucleus, passing through it, overlapping with it. And yet the atom does not collapse. The reason is that proximity and catastrophe are two different things. Being near the nucleus is just part of the electron's wave. The nucleus does not automatically capture the electron just because the wave is present there. For most atoms, the nucleus simply passes. The electron's wave overlaps the nucleus without anything dramatic happening, the same way a ripple on water passes through a piece of driftwood without the water being destroyed. But there is one condition where the nucleus does grab the electron, one rare strange event where proximity becomes real capture. And when that happens, the atom changes into something entirely different. That event is coming. But first, we need to understand what that closest approach actually looks like from a numbers standpoint. Imagine asking someone how close they live to a coffee shop. They say 2 miles. You picture their house, the street, the route between, a specific distance, a definite answer. Now ask an electron how close it gets to the nucleus. The electron cannot answer, not because the electron is shy, because the question assumes the electron has a specific position at all times, and it does not. This is the core confusion people run into when they hear about atomic collapse. The phrase, "How close can an electron get?" sounds like it should have a number attached. Like the electron has an orbit, and that orbit has a closest point, and you just need to calculate it. But the electron has no orbit. It has a wave function. And the wave function covers all of space, not just one path. Different parts of the wave function give different probabilities of finding the electron, at different distances from the nucleus. Some distances are more likely, some are less likely, but there is no single answer to the question of where the electron is, because the electron is spread across all distances simultaneously. This is a hard thing to sit with. It goes against every instinct. When you look at something, it is somewhere. Objects have locations. That is basic reality as we experience it. But at the quantum level, that basic reality does not apply. The electron's location is not hidden from us. The electron does not secretly have a position that we just cannot measure. It genuinely has no definite position until the moment it interacts with something. So when physicists talk about how close an electron gets to the nucleus, they mean something statistical. They ask, what is the most likely distance to find the electron if you measure it many times? That is called the most probable radius. And for the simplest atom, hydrogen, that radius has been calculated and confirmed with extraordinary precision. The most probable radius for a hydrogen electron in the ground state is roughly 53 trillionths of a millimeter. Physicists call this distance the Bohr radius. If you measured a hydrogen electron's position over and over, most results would cluster near that distance. Not all of them, just the most common. But the wave function extends all the way inward to the nucleus. There is a small probability of finding the electron much closer than the most probable radius. Right at the nucleus, even. The wave function has a value there. The probability is low but real. The twist is that finding the electron close to the nucleus on a given measurement does not mean the atom has collapsed. A measurement is just a measurement. Afterward, the electron goes back to its wave-spread state. The atom continues existing. One measurement result does not doom the system. Closest, in the quantum world, is a probability statement. It describes a range of possible outcomes weighted by likelihood. It is not a fixed, trackable path with a minimum distance marked on it. And this matters enormously for the collapse question. You cannot ask when the electron gets close enough to trigger collapse, because the electron does not approach the nucleus on a path. It simply has a probability cloud that includes some small amplitude near the nucleus at all times. The electron is already as close as it gets, all the time, everywhere in its wave function simultaneously, and that is somehow perfectly fine. Until we look at hydrogen more carefully and realize the wave function's behavior right at the nucleus is even stranger than that. Hydrogen is the simplest atom in the universe. One proton, one electron, no other particles to complicate things. Because of that simplicity, physicists have been able to calculate everything about it with incredible precision, down to distances that make the width of a human hair look enormous. And what they found is genuinely strange. In the hydrogen ground state, the electron's wave function is a smooth sphere around the nucleus. It is densest right at the nucleus. The wave function's value is highest exactly at the center, at zero distance from the proton. Read that again. The wave is strongest right at the proton, not at some safe distance away, right there, at the proton itself. That sounds like the atom is collapsed by definition. If the electron's wave is strongest at the nucleus, does that mean the electron is most likely to be at the nucleus? Here is where it gets subtle. Wave function density is not the same as probability of finding the electron there. To calculate the actual probability of finding the electron at a certain distance, you have to account for geometry, and geometry changes everything. Imagine you are searching for a friend in a city. The probability of finding them on one specific street corner is low, even if that corner is their favorite spot. Why? Because there are only a few square feet at that corner, but there are miles of streets at a 1 mile radius. More total area means more total places for them to be, which raises the overall probability for that distance, even if the chance per square foot is lower. The same logic applies to the electron around the nucleus. Right at the nucleus, the wave function is dense, but there is almost no volume there. A sphere of nearly zero radius has almost zero surface area, So even though the wave function value is high, the probability of finding the electron there, integrated over the tiny available volume, is nearly zero. As you move outward, the wave function value decreases, but the spherical shell grows in surface area. More area means more places to find the electron. At some point, these two effects balance, and then the area effect wins. The total probability of finding the electron at a given distance peaks at a specific distance from the nucleus. That peak distance is the Bohr radius, roughly 53 trillionths of a millimeter from the proton. That is the most likely place to find a hydrogen electron in the ground state. But the key point is that the wave extends all the way in. The probability does not drop to zero at the nucleus. It drops to nearly zero because the volume there is nearly zero, but the wave function itself has a real, non-zero value at the center. This means the electron is genuinely present at the nucleus, passing through it, overlapping with it. In a real quantum mechanical sense, the electron and the nucleus share space, and most of the time, nothing happens. The electron passes through, and the atom continues as if everything is normal, because at atomic energies, nothing nuclear occurs from that brief wave overlap. But most of the time is not all of the time. There are specific nuclei, specific atomic configurations where that overlap leads to something dramatic, where the nucleus reaches out and takes the electron permanently, turning the atom into something else entirely. That event is getting closer, but first something even more fundamental needs examining. The number itself, the Bohr radius, and exactly how impossibly small that 53 trillionths of a millimeter actually is. People hear that the electron overlaps the nucleus and immediately picture a crash, a collision, two things hitting each other, and one getting swallowed. It makes sense as an instinct. In everyday life, two objects occupying the same space means they have collided. But at the quantum level, occupying the same space is not an event. It is a state. The electron's wave function has amplitude at the nucleus. That means the electron has some probability of being detected there. But detection is not collision. The wave passing through the nucleus is not a physical impact. It is a mathematical overlap. And at the energy levels involved in ordinary atoms, that overlap produces no atomic consequence at all. Think of it this way. Sound waves can pass through a solid wall. When you hear music from another room, the sound wave has passed through the wall and emerged on the other side. The wave occupied the same space as the wall. But the wall did not collapse. The wave did not destroy the wall. Two different physical entities with different energy scales can share space without catastrophic interaction. The electron's wave passing through the nucleus is similar. The electron is an atomic scale phenomenon. The nucleus is a nuclear scale phenomenon. These two scales are completely different. The energy required to actually interact with the nucleus at the nuclear level is many millions of times larger than the energy of a normal atomic electron. The electron simply does not carry enough energy to trigger a nuclear event. So the wave passes through, the nucleus is there, the electron's probability cloud includes the nucleus in its range. And neither one registers the other in a way that causes anything to change. This is confirmed by observation. Hydrogen atoms are among the most studied objects in the history of science. They are stable for as long as measurements have ever been taken. The proton at the center does not swallow the electron, despite the wave overlapping it constantly. The atom persists. Now, here is the crucial distinction. What we just described is the normal case, an ordinary proton in an ordinary hydrogen atom. The proton does not have the right nuclear conditions to grab the electron. The energy balance does not favor capture, so nothing happens. But there are other nuclei, unstable ones, proton-rich ones, nuclei where the energy balance actually does favor grabbing an inner electron, where the overlap between the electron wave and the nucleus is not just a passing exchange, but an opportunity for a real nuclear interaction. In those nuclei, the wave overlap matters enormously. The inner electron, the one closest to the nucleus, the one whose wave is most concentrated near the center, becomes a candidate for something called electron capture, a process where the nucleus actually absorbs the electron for real and permanently. That process is rare, it requires specific nuclear conditions, and it transforms the atom completely. The element changes, the atom emits radiation. The whole atomic structure reorganizes. So the answer to why proximity does not equal crash has two parts. For ordinary stable atoms, the electron wave overlaps the nucleus without any nuclear interaction, because the energy scales are too far apart. For certain unstable atoms, the overlap does lead to a real event, because the nuclear energy balance favors it. The difference between those two situations reveals something remarkable about what a nucleus actually is and what electrons actually do when they get close. And that difference is about to become the center of the story. The Bohr radius is one of the most precisely measured and most important distances in all of science. It is roughly 53 trillionths of a millimeter. Written out as a number, it is 0.053 nanometers. Physicists use it as a fundamental unit of atomic distance. That number is almost impossible to picture directly, so let us build a scale. A human hair is about 80,000 nanometers wide. That means you could line up roughly 1.5 million Bohr radii across a single human hair. 1.5 million. The Bohr radius is to a human hair what a human hair is to about 18 miles of distance. Another way to feel it, if you enlarge the Bohr radius to the size of 1 foot, then on that same scale, a human being would be roughly the size of the distance between Earth and the Sun, about 93 million miles away. The atom is small in a way that human intuition was never built to handle. And yet, despite this impossible smallness, physicists can pinpoint the Bohr radius with extraordinary precision. They can confirm it through measurements of hydrogen's light spectrum, through scattering experiments, through atomic force microscopy, through a dozen other techniques. The number is real and well established. Here is why it matters for the collapse question. The Bohr radius is the most probable distance for the electron. Measurements cluster there, but the electron's wave function extends from 0 all the way to infinity. In principle, the electron has some probability of being found many times farther than the Bohr radius, and it has some probability of being found right at the nucleus. The Bohr radius is the peak of the probability distribution, the most likely outcome, but it is surrounded by a wide spread of other possible outcomes. What this tells us about collapse is important. The electron is not sitting at a fixed radius waiting to spiral inward. The electron has a spread of probabilities, and the most concentrated part of that spread sits at the Bohr radius. The electron is most likely to be about that far from the nucleus on any given measurement. Now consider what happens if you somehow tried to force the electron closer. You would be shifting the probability cloud inward, compressing it toward the nucleus. To compress a quantum wave into a smaller region, you need to add energy. The uncertainty principle demands it. Squeeze the electron tighter, and the energy goes up. For hydrogen in the ground state, the Bohr radius represents the natural balance point. Electric attraction pulls the electron inward, quantum pressure from confinement pushes it outward. The Bohr radius is where those two effects perfectly balance, creating the minimum total energy configuration. Below the Bohr radius, the quantum pressure wins and drives the energy higher. Above it, the electric force wins and also drives the energy higher. The Bohr radius is the bottom of an energy valley. The atom settles there because it has no mechanism to climb out. This is not a metaphor. The energy valley is real, calculated, confirmed. Every hydrogen atom on Earth sits at the bottom of that valley, at that radius, stable and unchanged. And now that you know where the electron sits, the next question is what happens to the total energy when you try to push the electron off that balance point toward the nucleus. The answer is more dramatic than most people expect. Every physical system settles at its lowest available energy. A ball rolls to the bottom of a hill. Water flows downhill. Heated gas radiates energy until it cools. The universe consistently moves toward lower energy states when given the chance. So you might expect an electron, given the chance, to settle as close to the nucleus as possible. The nucleus has positive charge. Opposites attract. The closer the electron, the stronger the attraction, the lower the electric potential energy. If energy always seeks a minimum, should the electric attraction is strongest? The answer is no, and the reason reveals something fundamental about how quantum mechanics protects matter. Electric potential energy does decrease as the electron moves closer to the nucleus. That part of the logic is correct. An electron right next to the nucleus has very low electric potential energy, much lower than an electron far away. If that were the only energy in the system, the electron would indeed crash inward. But it is not the only energy. The electron also has kinetic energy, the energy of motion. And here is the key. In quantum mechanics, an electron confined to a small region of space must have high kinetic energy. The uncertainty principle makes this unavoidable. When the electron is spread over a large region, its momentum is uncertain, but that uncertainty can be small. Low momentum uncertainty means low average kinetic energy, but when you squeeze the electron into a smaller region, the momentum uncertainty grows sharply. That means large possible momenta in all directions, and large momenta means large kinetic energy. So here is what actually happens when you try to push the electron closer to the nucleus. The electric potential energy drops, which looks favorable, but the quantum kinetic energy rises because the electron is being confined to a smaller space. At first, moving inward, the drop in electric energy is larger than the rise in kinetic energy, so the total energy decreases. This is why the ground state is where it is, at the radius where the total energy is lowest. But then, something flips. As the electron gets closer than the ground state radius, the kinetic energy starts rising faster than the electric energy falls. The total energy begins climbing again. Moving the electron closer actually costs more energy than you started with. The ground state sits exactly at the radius where total energy is minimized. Move the electron closer, and total energy goes up. Move it farther, and total energy also goes up. The ground state is the bottom of an energy valley with steep walls on both sides. To push the electron below the ground state, you would need to add energy to the system. A lot of it. You would need to put energy in to force the electron into a state that is energetically higher than the ground state, not lower. This is the crucial reversal. Closing in on the nucleus, past the ground state, means going uphill energetically. Matter does not roll uphill without a push, and there is nothing inside a normal atom available to provide that push. The electron stays at the ground state because the ground state is genuinely the lowest point, the true energy minimum. Going lower would require going higher first, and that is a door the atom keeps permanently closed. The next question is what happens when you press on that door harder than any ordinary atom can? The idea sounds backwards. You squeeze something smaller, you might expect it to have less energy. Like compressing a spring, storing energy, sure, but the compressing an electron make it more energetic overall. The answer comes down to what energy actually means for a quantum particle, and it is one of the most counterintuitive results in all of physics. For a classical object, like a compressed spring or a ball rolling on a slope, you can track position and momentum separately. You know where it is. You know how fast it is going. You can calculate the stored energy precisely. These are independent things. For a quantum particle, position and momentum are entangled in a deep way. You cannot specify both precisely. They trade off. If you constrain the position, the momentum becomes wildly uncertain. If you let the position be spread out, the momentum can be relatively calm. That trade-off has direct consequences for energy. Kinetic energy depends on momentum. Specifically, the kinetic energy of a particle goes up with the square of its momentum. Double the momentum, and kinetic energy quadruples. So when you confine an electron to a smaller space, raising its momentum uncertainty, the average kinetic energy does not just rise a little, it rises sharply. Here is the rough rule that comes out of the math. If you confine an electron to a region half the size, the kinetic energy it must carry goes up by roughly 4 times. Quarter the size, and kinetic energy climbs by about 16 times. That growth is steep, extremely steep, and it hits a breaking point very quickly as you push toward nuclear dimensions. The nucleus itself is roughly 100,000 times smaller than a typical electron orbit. If you forced the electron all the way into the nucleus, the confinement would be 100,000 times tighter. The kinetic energy required would be staggering. We are talking about energies in the mega-electron volt range, millions of times larger than the energies involved in ordinary atomic structure. No ordinary atomic process generates energy anywhere near that level. The electron cannot reach the nucleus through atomic mechanisms because getting there would require an impossible amount of energy injection from outside the system. So when people ask why the atom does not collapse, one clean answer is this: getting the electron to the nucleus would require more energy than the atom possesses by an enormous margin. The atom cannot collapse on its own because the energy required to complete the collapse does not exist within the system. The electron is already at the lowest possible energy configuration. Forcing it lower would cost energy the atom does not have. There is a satisfying symmetry here. The electric force pulls the electron inward, trying to reduce the atom's size. The quantum kinetic energy fights back, resisting confinement. These two tendencies fight to a standstill at the ground state. The atom settles there not because of a wall, but because of a perfect energy truce. That truce has held for every atom ever observed under normal conditions. But conditions can stop being normal. There are situations, rare and specific, where the nuclear energy balance shifts dramatically, where the nucleus gains the ability to pull off something the quantum energy barrier would normally prevent, where an electron gets taken. For real, for keeps. Understanding how that happens requires understanding exactly what changes when a nucleus becomes unstable. And that story is more dramatic than most people realize. Every atom that exists right now is sitting in a perfect standoff. Two forces pushing in opposite directions, locked in an exact tie, holding the structure in place. If either force shifted, the atom would move. But they do not shift, because the laws of physics lock them into balance at one specific distance. This balance point is not a coincidence. It is a mathematical result, inevitable from the equations governing charged particles in quantum mechanics. Every atom of the same type, anywhere in the universe, settles at the same balance point. Every hydrogen atom has the same Bohr radius. Every oxygen atom has the same inner electron distances. The balance is universal and exact. Let us walk through the standoff in detail. On one side, the electric force. The nucleus carries positive charge. The electron carries negative charge. Opposite charges attract. The force between them follows an inverse square law. Double the distance, and the force drops to 1/4. Halve the distance, and the force quadruples. The electric force grows stronger the closer the electron gets. It is always pointing inward, always pulling toward the nucleus. On the other side, quantum pressure. As the electron gets squeezed into a smaller region, the uncertainty principle demands higher momentum uncertainty. Higher momentum uncertainty means higher average kinetic energy. That energy pushes outward, resisting confinement. The closer the electron is held to the nucleus, the more kinetic energy it carries, and the harder it pushes back. Now, crucially, these two forces do not grow at the same rate. The electric attraction grows as the electron approaches the nucleus, but it grows according to an inverse square law. The quantum pressure grows faster, it increases more steeply with decreasing distance. So far away from the nucleus, the electric force dominates and pulls the electron inward. Very close to the nucleus, the quantum pressure dominates and pushes the electron outward. Somewhere in between, they are equal. That is the balance point. That is the ground state. At the ground state radius, moving the electron inward would cause the quantum pressure to win. Pushing it back out, moving the electron outward would cause the electric force to win. Pulling it back in, the electron settles at the balance point, the same way a marble settles at the bottom of a bowl. And here is the crucial part. The bowl has no hole at the bottom. There is no passage through the balance point into a lower energy region. The ground state is the minimum total energy. It is the bottom of the bowl with solid walls underneath. The atom persists because there is nowhere lower to go. The electron cannot fall below the ground state any more than a marble can fall below the bottom of a bowl by rolling harder. Now, this holds for ordinary atoms with ordinary nuclei. A proton sitting in a hydrogen nucleus does not grab the electron passing through. The nuclear energy conditions do not favor it. The electron overlaps the nucleus, and the nucleus does nothing but change the nucleus, make it proton heavy, make it unstable, create conditions where absorbing an electron would actually lower the nucleus's total energy. And suddenly that wave overlap, the electron's wave passing through the nucleus, becomes an opportunity, a real interaction, a capture. The atom transforms. An element becomes another element. The balance point disappears, and the atom emits radiation to announce what just happened. That event, electron capture, is exactly where we are headed next. And when you understand how an electron gets swallowed by the nucleus it has been circling for the atom's entire life, the entire story of atomic stability comes into sharp, dramatic focus. Hydrogen is the simplest atom. One proton, one electron. The Bohr radius, that most probable distance between them, sits at roughly 53 trillionths of a millimeter. That is already absurdly small. But hydrogen is not the whole story. As you move up the periodic table, atoms get heavier, more protons in the nucleus, more electrons surrounding it, and those inner electrons, the ones closest to the nucleus, get pulled dramatically tighter. Here is why. Electric force depends on charge. A nucleus with 2 protons pulls an inner electron with twice the force of a single proton. 6 protons pull 6 times as hard. 26 protons, like iron, pull 26 times as hard. The electric attraction scales directly with the number of protons in the nucleus. That stronger pull drags the inner electrons closer, significantly closer. In a heavy atom like lead, which has 82 protons, the innermost electrons sit at a distance roughly 82 times smaller than the hydrogen Bohr radius. That is not 82 times smaller in a vague sense. The math of quantum mechanics gives you that compression directly and precisely. So the inner electrons of heavy atoms are pressed up against the nucleus at distances that make hydrogen look like a wide-open field. They are genuinely close. Their wave functions overlap the nucleus with much higher density than a hydrogen electron ever achieves. The probability of finding them near the nuclear surface is real and measurable. And still, those heavy atoms hold together. Lead does not collapse. Gold does not dissolve. Despite the enormous nuclear charge and the correspondingly compressed inner electron orbits, the quantum energy balance holds. The reason is the same balance we examined in hydrogen, just scaled up. The stronger the nuclear charge, the deeper the electric potential energy well. But the deeper the well, the higher the kinetic energy the electron must carry to occupy that ground state. The two effects track each other. Stronger pull, stronger quantum pushback. The balance point shifts closer to the nucleus, but it remains a balance point. This is one of the more remarkable things in all of atomic physics. The same mechanism that protects a hydrogen atom from collapse protects lead. The same mathematical relationship between electric attraction and quantum kinetic energy that sets the Bohr radius in hydrogen sets the inner electron radius in every element on the periodic table. the equation scales cleanly. There is an interesting side effect of this scaling. In the heaviest atoms, the inner electrons travel so fast that their speed becomes a meaningful fraction of the speed of light. When that happens, the theory of relativity has to be included in the calculation. Without relativistic corrections, the predicted inner electron distances for gold and mercury come out wrong. With those corrections, the predictions match experiment precisely. Gold's famous yellow color is actually a relativistic effect. The relativistic compression of inner electrons shifts the energy gaps between shells, which changes which wavelengths of light the atom absorbs, which changes the color you see. Without quantum mechanics and relativity working together, gold would look silver. Every solid object you see is the product of that balance, scaled across every element in existence. But the inner electrons of heavy atoms do something else interesting when that balance is tested by an unstable nucleus, something that takes proximity to a whole new level. The nucleus of a gold atom contains 79 protons, all of them positively charged, all of them crammed into a space smaller than a football stadium's marble. Like charges repel violently. The repulsion between those protons is enormous. So why does the gold nucleus not explode? That is actually a separate question from atomic collapse, and the answer involves a force that most people have never heard of: the strong nuclear force. This force operates only at extremely short distances, shorter than the width of a proton, but within that range it is extraordinarily powerful. It binds protons and neutrons together with a grip that overwhelms the electric repulsion between protons. The strong force is what holds the nucleus together despite its protons trying to push apart, and it has nothing to do with electrons. The nucleus and the electron cloud are two separate systems, held together by different forces, operating at different energy scales. What keeps the gold atom from imploding as a whole is the combination of a stable nucleus held by the strong force and inner electrons held at their quantum-determined distances by the balance between electric attraction and quantum pressure. Both systems, nucleus and electron cloud, are independently stable. The strong force locks the nucleus. The uncertainty principle locks the electrons at their ground state radii. Together, they make gold an enduring, stable structure. Now here is what makes heavy atoms genuinely different from hydrogen in one important way. In hydrogen, the single electron has so much space relative to the nucleus that the overlap between the electron wave and the nuclear volume is tiny. In gold, the inner electrons are pressed so close that the overlap is significantly larger. The electron wave is physically concentrated in the region near the nucleus to a much greater degree. That increased overlap matters for a specific and rare process. Remember that the electron wave passing through the nucleus usually produces no interaction because the energy scales of atomic electrons and nuclear reactions are far apart. For a hydrogen electron, the energy gap is so large that capture is essentially impossible for a stable proton. But the inner electrons of a heavy atom carry more kinetic energy. They sit deeper in the electric potential well. They are faster, more energetic, more relativistic. They overlap the nucleus more densely. For nuclei that are already on the edge of instability, those factors combine to make a real difference. The nucleus of a heavy unstable atom and one of its inner electrons interact differently than a proton and a hydrogen electron. The energy accounting is different. The likelihood of capture is different. This is the bridge between stable heavy atoms and the rare dramatic event of electron capture. The sheer closeness of the inner electrons to the nuclear surface, a closeness forced by the large nuclear charge, is part of what makes certain heavy atoms candidates for this process. Gold and lead themselves are stable. Their nuclear energy balance does not favor electron capture. But nearby elements on the periodic table, elements with slightly different proton-to-neutron ratios, fall on the other side of that line. And for them, the proximity that the large nuclear charge creates becomes the setup for a transformation. How a nucleus tips over that line, and what happens when it does, is something that physicists track element by element, and the consequences reach far beyond the atom itself, all the way into medical imaging, industrial measurement, and our understanding of stellar evolution. What comes next changes the story completely. Up to this point, the story has focused on a single electron and how it sits in its ground state, protected by the uncertainty principle, balanced against the nucleus. But most atoms have more than one electron, and adding more electrons raises a new question immediately. If the ground state is the lowest energy level, why do all the electrons not just pile into it? Why do heavier atoms spread electrons across multiple shells instead of cramming them all as close to the nucleus as possible? The answer is one of the strangest rules in all of physics, the Pauli exclusion principle. Wolfgang Pauli proposed it in 1925, and at the time it seemed like a strange technical rule. He said that no two electrons in the same atom can have the same complete set of quantum properties. Every electron must be distinct. Electrons have 4 such properties: their energy level, their orbital shape, their orbital orientation, and something called spin. Spin is a property of quantum particles that has no classical equivalent. Think of it loosely as an internal arrow that can point either up or down. 2 electrons can share the same energy level, the same orbital shape, and the same orientation, but only if their spins are opposite. One up, one down. That exhausts the available combinations for that particular configuration. Once both spin states in a given configuration are filled, the next electron cannot join. The slot is full. It must go to the next available configuration, which means a slightly higher energy level. And so atoms build outward, shell by shell, each shell filling before the next begins. This is why the periodic table has the shape it does. The first shell holds 2 electrons. The second holds 8. The third holds 18. Each new element has 1 more proton and 1 more electron than the last, and that extra electron has to find the next available slot. The structure of chemistry, the reason different elements have different properties, the reason some atoms bond readily and others barely react at all, traces directly back to Pauli's rule. Now connect this to the collapse question. If the Pauli exclusion principle did not exist, every electron in a heavy atom would crowd into the ground state, all of them pressing as close to the nucleus as the balance point allows. The electrons would pile in, the atom would shrink to roughly the size of a hydrogen atom, no matter how many electrons it contained. With Pauli's rule, each electron occupies a distinct state. Higher states are farther from the nucleus. The atom grows as more electrons are added. Elements get physically larger as they gain electrons, at least in a rough sense, across the periodic table. And here is the connection to solid matter. The Pauli exclusion principle is also the reason solid objects cannot pass through each other. When 2 atoms are pressed together, their electron clouds begin to overlap. The outer electrons from both atoms start competing for the same region of space. Pauli's rule forbids them from occupying the same state. The result is a powerful repulsive force between the atoms. That repulsion is what you feel when you press your hand against a wall. The wall feels solid because electrons refuse to share quantum states. The Pauli exclusion principle is the force behind every surface you have ever touched. And there is one more thing it does that nobody usually talks about. It determines which electrons are the most vulnerable to being captured by the nucleus. And that vulnerability is the next piece of the story. Before we reach the event of electron capture, there is a tool built on the gap between electron shells that most people use without ever thinking about how it works: X-ray machines. And understanding them sets up the electron capture story perfectly. When electrons fill their shells around the nucleus, each shell has a specific energy. The innermost shell, closest to the nucleus, has the lowest energy. Electrons there are tightly bound, held deep in the electric potential well. Outer shells have higher energies. Those energy gaps between shells are precise, fixed, specific to each element. Now imagine something knocks an inner electron completely out of an atom. A high-speed electron from an X-ray tube smashes into the inner shell and ejects one of its electrons. Suddenly there is a vacancy, an empty slot in the innermost shell. That vacancy does not last. An outer electron drops down to fill it almost instantly. The outer electron had more energy. The inner slot has less energy. When the electron drops down, it must release the energy difference, and it releases that energy as a photon, a packet of light. The energy gap between shells in heavy atoms is enormous, hundreds or thousands of times larger than the gaps that produce visible light. Those high-energy photons fall in the X-ray range. That is why X-ray machines work. They knock out an inner electron, an outer electron falls to fill the gap, and the emitted photon is an X-ray that can pass through soft tissue but gets blocked by dense bone. Every X-ray image ever taken is a record of electrons falling between shells. Now here is why this matters for the next part of the story. The same gap structure, the same energy bookkeeping between inner and outer shells, plays a central role in electron capture. When a nucleus captures an inner electron, it creates exactly the same kind of vacancy. The inner slot is now empty. Outer electrons fall inward to fill it. Energy is released. The difference is how the inner electron disappeared. In an X-ray machine, an outside particle kicked it out. In electron capture, the nucleus itself absorbed it. Both events leave the same signature, a cascade of outer electrons dropping inward, each one releasing a photon as it falls. After electron capture, the atom emits a burst of characteristic X-rays, announcing the event to any detector nearby. This is how scientists observe electron capture happening in radioactive samples. They watch for the characteristic X-ray signatures of specific elements. The energy gap between shells is not just a property of the atom's structure, it is also a communication channel. Every time an electron falls between levels, the atom broadcasts a photon at a precise frequency that identifies exactly which element it is and exactly which transition just occurred. This atomic fingerprinting is one of the most powerful tools in modern science. It lets researchers identify elements in distant stars, track radioactive decay in medical labs, and detect specific atoms and materials without touching them. The energy gaps that Bohr first guessed at in 1913 are now the foundation of entire industries. But the most dramatic use of that gap structure, and the most dramatic way an inner electron can disappear, is electron capture itself, the moment when the nucleus reaches out and permanently absorbs one of its own electrons. What exactly happens inside the nucleus at that moment is something most people have never heard described in full. Everything up to this point has been about why atoms stay stable, why electrons do not crash, why the quantum balance holds. But stability has exceptions, and one of those exceptions is genuinely strange. It is called electron capture, and it is one of the few cases in all of physics where an electron really does get taken by the nucleus it has been orbiting. The setup requires a specific kind of nucleus, a proton-rich nucleus, one that has too many protons relative to its neutrons. The nucleus exists in a state of energetic tension. It wants to lower its energy. One of the ways it can do that, in certain specific cases, is by converting a proton into a neutron. Converting a proton into a neutron requires absorbing an electron and releasing a neutrino, a nearly massless particle that barely interacts with anything and flies away at nearly the speed of light. The process is governed by the weak nuclear force, the same force responsible for certain types of radioactive decay. The weak force is short range. To use it, the electron has to be very close to the nucleus. Specifically, it has to be overlapping the nucleus, which is exactly what we established happens all the time in the ground state wave function. The inner electron's wave passes through the nuclear volume constantly. For most nuclei, that overlap produces nothing. The nuclear energy balance does not favor the conversion. A proton becoming a neutron would not lower the energy of the system, so it does not happen. But for proton-rich unstable nuclei, the energy calculation flips. Absorbing an inner electron and converting a proton to a neutron would lower the nucleus's total energy. The system favors the change, and when the electron's wave overlaps the nucleus at the right moment, the weak force can act. The electron is absorbed. This is a probabilistic event. The electron does not get absorbed on every pass. The probability per overlap is tiny, but the electron's wave overlaps the nucleus enormously many times per second. Eventually, given enough overlapping attempts, the weak interaction fires. The electron disappears into the nucleus. The inner electrons, the ones in the first and second shells, have the highest probability of being captured because their wave functions are most concentrated near the nucleus. The very electrons that the Pauli exclusion principle placed closest to the nucleus are the most likely candidates for capture. This is the moment the title of this story becomes literal. The electron gets as close as physically possible. It enters the nucleus, and it does not come back out. But the aftermath is almost more interesting than the capture itself. The element changes. The nucleus changed its proton count. A completely different element now occupies the space where the original atom was. The electron cloud has to reorganize, and the reorganization announces itself to the universe in a way that detectors can pick up clearly. If you have ever wondered whether there is a process in nature where an atom genuinely transforms into another atom without any explosion or violent collision, electron capture is your answer. It happens quietly, invisibly, and it turns one element into another element with a thoroughness that nothing short of nuclear physics can match. The moment of electron capture lasts an incomprehensibly short time, but inside that moment, something fundamental about the nucleus changes permanently. Before capture, the nucleus has a specific number of protons and neutrons. The electron approaches, carried along by its wave function, overlapping the nuclear volume in the way that ground-state electrons always do. For an ordinary stable nucleus, nothing happens. But for a proton-rich, unstable nucleus, something is ready to fire. The weak nuclear force acts. This force is responsible for a class of nuclear transformations where particles change type. It can turn a neutron into a proton, or as in this case, help turn a proton into a neutron by absorbing an electron. When the electron enters the nuclear volume and the weak force acts on it, the electron and one specific proton interact. The electron ceases to exist as a free electron. The proton ceases to exist as a proton. What emerges instead is a neutron and a neutrino. The neutron stays in the nucleus. It simply replaces the proton that was there, adding to the neutron count and reducing the proton count by exactly 1. The neutrino, which has almost no mass and interacts with almost nothing, escapes at nearly the speed of light and is essentially gone forever from the atom's perspective. The nucleus has now changed its proton count. Since the chemical identity of an element is determined entirely by the number of protons in its nucleus, the element has changed. This is called transmutation. The atom is now a different element. The new nucleus has the same total number of nuclear particles it had before, protons plus neutrons combined, but the ratio has shifted. 1 proton became 1 neutron. If the capture was energetically favorable, the new nucleus is more stable than the old one. The system has moved to a lower energy state. One of the best-known examples of this involves potassium. A specific form of potassium, common in the food we eat, undergoes electron capture at a steady, measurable rate. When it does, it becomes argon. The argon accumulates in rock formations over millions of years, and by measuring how much argon is present relative to the remaining potassium, geologists can determine the age of rocks. This technique has been used to date some of the oldest known materials on Earth and the Moon. The weak nuclear force, the electron wave function overlap, and a simple proton-to-neutron conversion combine to give scientists a clock that runs inside every rock on the planet. But the transformation of the nucleus is only part of what happens. The atom as a whole still has all its original electrons, except the one that was just absorbed. The electron configuration now has a hole in the innermost shell. That hole triggers a cascade that produces a very specific kind of radiation. A cascade that scientists have learned to read like a fingerprint, identifying exactly what element was created and confirming the capture occurred. That cascade is what makes electron capture visible to the outside world, and it reveals something beautiful about how the atom reorganizes itself after losing one of its closest members. Of all the ways an atom can change, electron capture is among the quietest. No explosion, no burst of visible light, no dramatic eruption of matter. From the outside, the atom simply becomes something else. That silence is part of what makes electron capture so strange. Most radioactive decay events announce themselves loudly. Alpha decay throws out a helium nucleus. Beta decay ejects a fast-moving electron from the nucleus itself. Gamma decay blasts out high-energy photons. Each of these is energetic, detectable, dramatic. Electron capture ejects only a neutrino, and neutrinos are the most antisocial particles in the universe. They carry no electric charge. They have almost no mass. They interact with normal matter only through the weak force, which operates at ranges far smaller than an atomic nucleus. A neutrino can pass through a wall of lead 1 light-year thick and emerge on the other side, essentially unaffected. From a detector sitting outside the atom, the neutrino is invisible. It has already left the scene at near light speed before any measurement could catch it. The only direct signal from the capture itself is gone. What remains is the aftermath. A nucleus with 1 fewer proton and 1 more neutron than it had before. An electron configuration with a gap in the innermost shell, and the cascade of outer electrons falling inward to fill that gap. That cascade, as we established, releases characteristic X-rays. These X-rays are the fingerprint of the new element, the daughter atom that was born when the nucleus transformed. Detectors catch these X-rays and confirm both the original element and the new one. But there is something deeper about this quiet transformation that matters for how we understand matter. An atom contains its own electrons for its entire life, the same electrons held in place by the same quantum balance, persisting as long as the nucleus remains stable. And then, for a specific class of unstable atoms, the nucleus quietly reaches out during one of those endless overlapping passes of the inner electron wave and takes one. The atom's own electron becomes part of the nucleus. The atom becomes a fundamentally different element without any outside force being applied. The transformation is internal, self-contained, a chemical element rewriting its own identity using a tool it has always carried but almost never uses. This happens on timescales that vary enormously by element. Some nuclei capture an electron within seconds of forming. Others wait for millions of years before the weak force acts. The half-life of electron capture for different isotopes spans from fractions of a second to timescales longer than the current age of the universe. Each of those timescales is a fixed, calculable result of the nuclear energy balance and the strength of the weak interaction for that specific nucleus. The physics determines the clock. The clock runs at exactly the predicted rate, every time. There is a kind of precision in this that is almost hard to accept. A nucleus waiting millions of years for the right moment, the moment when the quantum overlap and the weak force and the energy balance all align, and then acting instantly and irrevocably. A proton becomes a neutron. An element becomes another element. And the only witness is a neutrino that is already 1 trillion miles away. The resulting atom is quieter still, but not completely quiet, because that inner shell vacancy broadcasts a signal in X-rays that announces exactly what just happened. The nucleus has just absorbed an inner electron. The atom is now a different element, but the electron cloud has not caught up yet. The outer electrons still think they are surrounding the original nucleus, and one of them is about to make a very fast trip inward. In the innermost shell, there is now a vacancy, an empty slot where the captured electron used to sit. That vacancy is an invitation. Outer electrons exist at higher energies, and the first shell sits at a lower energy. The difference between those two energies is significant. In a heavy atom, that energy gap can be thousands of times larger than the energy of visible light. An electron from the second shell drops down to fill the vacancy. In doing so, it releases the energy difference as a photon. For heavy atoms, that photon lands in the X-ray range of the electromagnetic spectrum. It arrives at a very specific energy determined precisely by the difference between the energy levels of the two shells involved. The first photon is released, but now there is a new vacancy, this time in the second shell. Another outer electron drops to fill that gap. Another photon released. Another X-ray emitted. The cascade continues outward, shell by shell, each transition releasing a photon at an energy specific to that element's shell structure. This cascade of X-rays is called the characteristic X-ray emission of the daughter element. Every element has a unique set of shell energies. Every set of shell energies produces a unique set of photon frequencies during the cascade. The X-rays are a fingerprint. By measuring their energies precisely, a detector can identify exactly which element produced them and exactly which transitions occurred. This is how scientists observe electron capture in a laboratory. They cannot detect the neutrino directly, but they can detect the characteristic X-ray cascade that follows the capture. The X-rays arrive, the detector logs their energies, and the data confirms that a specific nucleus captured an inner electron and became a specific daughter element. The precision of this technique is extraordinary. The energy of each photon in the cascade matches the calculated shell energy differences for the daughter element to within a fraction of a percent. The match between theory and measurement has been confirmed for dozens of elements across the periodic table. There is something remarkable about the information contained in those X-rays. They reveal the shell structure of the atom, the exact energies of each level, the gaps between them, all encoded in the energies of the emitted photons. A single electron capture event broadcasts a complete atomic biography in X-ray light. Scientists use this not only to study radioactive decay, but also to probe the structure of atoms that are difficult to study by other means. The characteristic X-ray cascade is so precise that it can distinguish between atoms with nearly identical chemical behavior but different nuclear compositions. The X-ray flash after electron capture is brief. The cascade happens on timescales far shorter than a billionth of a second. The entire reorganization of the electron cloud, from vacancy to filled shells, completes almost instantly. And then the atom settles into its new identity, the daughter element, with its electron cloud balanced around the new nucleus. The atom's story could end there, but electron capture is more than a curiosity of nuclear physics. Scientists discovered they could put it to work, and the application they found has helped save millions of lives. The same process that quietly turns one element into another inside a rock is now being used inside hospitals to take some of the most detailed images of living tissue ever produced. Positron emission tomography, known as a PET scan, works by introducing a radioactive substance into the body. That substance decays while inside the patient. The decay releases detectable radiation that scanners around the patient pick up. By mapping where the radiation comes from, doctors get a precise image of which tissues are active and which are not. The radioactive substances used in PET scans are often produced through a process very close to electron capture. Some are produced by bombarding stable atoms with particles that force them into a proton-rich state, primed for the kind of nuclear transformation we have been describing. The result is an unstable nucleus that either undergoes electron capture or a closely related decay called positron emission, where the nucleus emits a positive version of the electron instead of absorbing one. Both electron capture and positron emission reduce the proton count by 1 and increase the neutron count by 1. There are two competing paths to the same destination. Which path a given nucleus takes depends on the specific energy balance of that nucleus. The most widely used tracer in PET scanning, a modified form of glucose, contains a nucleus that decays by positron emission in this fashion. The positron immediately meets an ordinary electron in the body's tissue, and the two annihilate each other, producing two gamma-ray photons flying in exactly opposite directions. The PET scanner detects both photons simultaneously and traces the line between them back to the point of annihilation. Do this millions of times, and you build a three-dimensional map of wherever the tracer accumulated. Cancer cells consume glucose at a much higher rate than normal cells. The tracer concentrates there. The PET scanner lights up exactly where the cancer is. Doctors can see tumors with precision that traditional imaging cannot match. None of this would be possible without the nuclear physics of proton-to-neutron conversion. The entire medical imaging chain, from the radioactive tracer to the gamma-ray detection to the three-dimensional map of metabolic activity, rests on the same weak force interaction that we traced back to electron capture. The electron that gets swallowed by a nucleus in a radioactive tracer is doing its part in a process that reaches from fundamental particle physics all the way to a doctor's diagnosis of cancer in a patient's lung. Science rarely travels in straight lines. The discovery that electrons overlap the nucleus, the understanding of how the weak force can act on that overlap, and the technical ability to produce specific unstable isotopes on demand all had to combine before PET scanning became possible. None of those discoveries were made with medical imaging in mind. They came from pure physics, driven by curiosity about why atoms behave the way they do. But the deepest application of everything we have learned about electrons and nuclei is not in medicine. It is in a prediction so extreme that scientists doubted it could ever be tested. A prediction about what happens to atoms when the nuclear charge is not just heavy, not just unstable, but pushed to an extreme that ordinary matter never reaches. Throughout this story, the nuclear charge has been a variable that changes the electron's distance from the nucleus. More protons means stronger pull, compressed inner electron orbits, faster relativistic electrons, and increased wave function overlap with the nucleus. But what happens if you push that charge far beyond any element that naturally exists? What if the nuclear charge became so strong that the ordinary rules of atomic structure begin to break? This is not a fantasy scenario. Physicists worked out the math for it, and the prediction is genuinely strange. In standard quantum mechanics, the equation that governs the electron's wave function in an atom requires the nuclear charge to stay below a specific limit. That limit, calculated precisely from the fundamental constants of physics, corresponds to a nucleus with roughly 137 protons. No element with that many protons exists in nature. The heaviest stable elements have around 82 protons. The heaviest artificially created elements reach into the 110 to 118 range, and all of them are intensely unstable, existing for fractions of a second. But in principle, if you could assemble a nucleus with 137 or more protons and keep it from flying apart instantly, the equation that describes the inner electron would behave differently. The solutions would become unstable. The ground state would no longer be a simple, stable energy minimum. Beyond this limit, the theory predicts that the electron binding energy reaches the threshold where electrons and positrons can be spontaneously created from the vacuum of space itself. The electric field of the superheavy nucleus becomes strong enough to pull a real electron from what physicists call the quantum vacuum, a region of space that seethes with virtual particle pairs constantly blinking in and out of existence. When the field is strong enough, one of those virtual electrons becomes real. Captured by the nucleus, the partner positron flies away. This is not a gradual process. It is predicted to be a dramatic, spontaneous restructuring of the vacuum around the atom. Physicists call this state atomic collapse. The specific use of the word collapse here is different from the collapse we discussed in chapters 1 through 5. This is the collapse of ordinary atomic physics itself, the point where the standard description breaks down and something new takes over. The number 137 appears naturally in physics in another context as well. It is related to the fine structure constant, the fundamental number that sets the strength of the electromagnetic force. An atom with 137 protons sits at a threshold set by the deepest constants in nature. That is not a coincidence. The threshold exists precisely because of the relationship between electric force strength, electron mass, and the speed of light. For decades, this remained purely theoretical, a prediction sitting beyond the reach of any experiment. The heaviest nuclei that could be made were far too short-lived and too small in charge to test it. The atomic collapse regime existed only on paper, until a team of physicists found a way to test the prediction without ever making a super-heavy nucleus at all. What they found in 2013 sent a wave through the physics community, and they did it using a material that most people associate with pencils, not particle physics. Graphene is a single layer of carbon atoms arranged in a hexagonal grid, like a sheet of chicken wire 1 atom thick. It was first isolated in 2004 by researchers at the University of Manchester using ordinary adhesive tape and a pencil, and it immediately became one of the most studied materials in the history of physics. Electrons inside graphene behave strangely. They move through the material at speeds far below the speed of light, but the equations that describe their motion look identical to the equations for particles moving at the speed of light. The graphene electrons effectively behave as if they are massless, as if they are governed by relativistic quantum mechanics, even at low speeds. This makes graphene a kind of physics simulator. Phenomena that would normally require extreme energies or conditions can be observed in graphene at room temperature using ordinary laboratory equipment. Physicists began to realize they could use graphene to test ideas from high-energy physics without a particle accelerator. In 2013, a team of researchers at the Massachusetts Institute of Technology and the University of California used a scanning tunneling microscope to place small clusters of calcium dimers, paired calcium atoms, on a graphene sheet. These calcium clusters carried a positive charge. By varying the number of calcium atoms in the cluster, the researchers could control the effective charge that the graphene electrons experienced. As they increased the charge of the cluster, they watched what happened to the graphene electrons nearby. At a certain threshold of charge, the behavior of the electrons changed dramatically. The electrons began to exhibit the signatures predicted for atomic collapse. Their wave functions shifted. States appeared that matched the theoretical predictions for electrons in a super-heavy nuclear field. The team published their results in the journal Science. They had directly observed, for the first time, the physics of atomic collapse in a real experiment. The state that theorists had predicted for hypothetical super-heavy nuclei was real. It could be studied. It behaved exactly as the theory said. The result was striking for 2 reasons. First, it confirmed a decades-old theoretical prediction in quantum mechanics and relativistic physics that had never been experimentally accessible before. The theory, which connected the fine structure constant, the electron's behavior in extreme fields, and the spontaneous creation of electron-positron pairs from the vacuum, turned out to be correct where it could be tested. Second, it demonstrated the power of graphene as a physics laboratory. Phenomena that belonged to the domain of nuclear physics and high-energy particle physics could be recreated and studied in a carbon sheet at room temperature. The same equations govern the massless electrons in graphene as govern electrons near a supercharged nucleus, just at a scale where human-made instruments can probe them directly. The graphene experiment did not create a collapsing atom in the traditional sense. The calcium cluster was not a nucleus. The graphene electrons were not ordinary atomic electrons, but the mathematics was the same. The signatures were the same, and the observation confirmed something profound. The limit built into the laws of physics, the threshold beyond which ordinary atomic theory breaks, is real. It is not just a mathematical artifact. Something physically different happens when you cross it, something that turns out to be even stranger when you look closely at what atomic collapse actually looks like in the graphene system. When the researchers watched their instruments as they increased the charge on the calcium cluster, they were looking for specific signals. Quantum mechanics predicted what should happen, step by step, as the effective charge climbed toward the collapse threshold. Below the threshold, the graphene electrons near the cluster behaved normally. Their wave functions spread out smoothly. The energy levels matched standard quantum predictions for electrons in a charged field. Everything looked ordinary. Then the charge crossed the threshold. The scanning tunneling microscope, which images surfaces by measuring tiny electrical currents at the scale of individual atoms, showed a dramatic change in the electron density near the cluster. A new type of state appeared. The electrons began to accumulate much closer to the cluster than they had before. Their wave functions showed a concentration near the charge source that matched exactly the theoretical prediction for the collapsing state. In the theoretical picture, the atomic collapse state is one where the electron's energy level dives below a threshold called the negative energy continuum. When that happens, the electron can no longer be described as a bound state sitting above the vacuum. It merges with a class of states that exist at the edge of particle-antiparticle creation. The electron effectively becomes part of the charged region, and a positron is emitted. In the graphene system, the equivalent phenomenon produced a measurable resonance in the electron density near the cluster. A peak in the local density of states, sitting at a specific energy, that appeared suddenly when the charge threshold was crossed and disappeared when the charge dropped back below it. The physicists could tune the threshold by adding or removing individual calcium atoms. One fewer atom, and the resonance was gone. One more atom and it returned. The transition was sharp, reproducible, and exactly where the theory predicted it would be. That reproducibility was what stunned the community. Theoretical predictions in this regime had never been tested before, because the conditions required seemed impossibly extreme. Nuclei with 137 protons do not exist in any stable form. Nobody had ever seen atomic collapse. And yet here it was, in graphene, in a university laboratory, with a scanning tunneling microscope and some calcium atoms. The result validated not just one prediction, but a whole class of theoretical results that connect atomic physics, relativistic quantum mechanics, and the physics of particle-antiparticle pairs near strong fields. These ideas had been developed over decades by theorists who had no way to test them. The graphene experiment closed that gap in a single set of measurements. What makes the graphene result especially striking is the role the material plays. Graphene is not a nucleus. It is not a particle accelerator. It is a sheet of carbon atoms. But the mathematical structure of electron behavior in graphene is so similar to the mathematical structure of relativistic electrons near extreme charges that the same physics plays out in both systems. Graphene is, in this sense, a working analog computer for extreme atomic physics. This is a pattern that appears repeatedly in physics. The same equations show up in wildly different physical systems. When that happens, studying the easier system teaches you something real about the harder one. What was learned in graphene applies directly to our understanding of electrons in the most extreme environments in the universe. Environments that exist not in any laboratory, but deep inside the most violent objects in space. We have spent much of this story inside the atom, watching the electron and the nucleus interact. But the same rules governing that interaction reach outward. They determine the behavior of every solid surface you have ever encountered. When two atoms are pushed toward each other, their electron clouds begin to overlap. The outer electrons of both atoms start competing for the same region of space. And here is where the Pauli exclusion principle, which we met earlier as the rule that fills atomic shells, becomes a physical force between atoms. When two electrons from different atoms are forced into the same region, they cannot occupy the same quantum state. The exclusion principle forbids it. To coexist in overlapping space, they would have to occupy different states. But the available low-energy states are already taken. The only available states are higher energy ones. Forcing two atoms close together means forcing their electrons into higher energy configurations. That takes energy from outside. The atoms resist. They push back against the compression. That resistance is what we experience as the hardness of solid objects. The floor holds your weight because the atoms in the floor resist the compression that your weight imposes. The wall stops you because its atoms refuse to let your atoms pass through them without an enormous energy cost. Every surface in the world, every solid thing, every boundary between one material and another is maintained by the Pauli exclusion principle, working at the atomic scale. This is one of the more profound connections in all of physics. The rule that prevents electrons in a single atom from all collapsing into the lowest state is the same rule that prevents matter from collapsing into itself at every scale. The Pauli exclusion principle operates at the atomic level, at the molecular level, at the solid material level, and even at the astrophysical level. In the cores of dead stars called white dwarfs, the Pauli exclusion principle is the only thing preventing total gravitational collapse. The star's gravity crushes matter so intensely that atoms are no longer intact. Electrons and nuclei form a dense soup. But even in that soup, the Pauli exclusion principle holds. The electrons resist being compressed into the same states. They push back against gravity. The star stabilizes at a size roughly equal to Earth, held up entirely by quantum mechanical pressure. If the star is massive enough, gravity eventually wins. The exclusion principle cannot hold against enough weight. The electrons are forced into the nuclei. The star collapses further and becomes a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh as much as a mountain. The collapse scenario we started this story with, an electron spiraling into a nucleus, turns out to be a metaphor for collapses happening at every scale in the universe. Atoms stay intact because of quantum pressure. Solids stay solid because of the same pressure applied between atoms. White dwarfs stay stable because of the same pressure applied between electrons in a stellar remnant. And when that pressure finally fails, the consequences are some of the most dramatic events in the cosmos. The electron's refusal to crash is, at root, the universe's refusal to collapse. Understanding one is understanding the other, and understanding both leads to the most dramatic question of all: what would actually happen to matter if the quantum ground state somehow did not exist? Take any ordinary moment of your day and pull it apart at the smallest scale. You're sitting somewhere. The chair holds your weight. The floor holds the chair. The air around you stays air. Your body maintains its shape. Chemistry runs on schedule. Cells divide, neurons fire, proteins fold. All of that, every single piece of it, depends on atomic stability. Each atom in your body, and there are roughly 7,000 trillion of them, is stable because the quantum ground state holds. Each one maintains its structure for the same reason we traced through this entire story. The wave function settles at the balance point between electric attraction and quantum pressure. The electron stays where it is. The atom persists. Now multiply that across the 7,000 trillion atoms in your body, and the number becomes almost religious in scale. 7,000 trillion independent quantum balance acts, running simultaneously, continuously, every moment you exist. Every one of them holding. Your body is not a solid object in the intuitive sense. At the atomic scale, it is almost entirely empty space. The nuclei of your atoms, if you could line them up, would be separated by distances that dwarf their own size by factors of 100,000. You are mostly vacuum, held in a human shape by quantum rules that operate at distances your senses could never directly perceive. What gives your body its shape is the electron cloud structure of your atoms. The outer electrons determine how atoms bond to each other. Those bonds determine molecular shapes. Molecular shapes determine protein structures. Protein structures determine cell functions. Cell functions determine you. Pull the quantum stability out, and the chain collapses instantly. Atoms lose their ground states. Electrons spiral inward in 16 trillionths of a second. Molecules dissolve because the bonds holding them together require stable electron clouds. Chemistry stops. The remarkable thing is not that the universe has quantum mechanics. The remarkable thing is that quantum mechanics produces stable atoms, and stable atoms produce chemistry, and chemistry produces the staggering complexity of everything that exists, including the ability to ask questions about why it exists at all. This is the connection that most physics explanations skip. The uncertainty principle is usually described as a strange limitation on measurement, a quirk of quantum weirdness, but its most important role is simpler and more profound than that. It prevents matter from collapsing, it gives electrons a floor, it keeps atoms intact. It makes chemistry possible, it makes you possible. Every material property you have ever relied on, the strength of steel, the flexibility of a rubber band, the hardness of a diamond, traces back to the same quantum pressure that stops an electron from falling into a hydrogen nucleus. The scale is different, the material is different, the underlying rule is identical. And there is one final thought experiment that brings this into sharp focus. If you could, hypothetically, turn off the uncertainty principle for a fraction of a second, what would happen to matter? The answer unfolds faster and more completely than anything you have probably imagined, and it reveals just how precarious the universe's stability actually is, held together by rules that could, in principle, have been different. Imagine the uncertainty principle simply stops applying. Not gradually, instantly, everywhere. For one moment, electrons are allowed to have both a precise position and a precise momentum. The quantum flaw vanishes. The cascades would begin everywhere at once. In every atom in the universe, the electron clouds would immediately begin to collapse inward. Without quantum pressure resisting confinement, there is nothing to balance the electric attraction pulling electrons toward the nucleus. The electrons spiral. The classical collapse that terrified physicists in the early 1900s plays out in full. The timescale is 16 trillionths of a second, less than the time it takes light to cross a human hair. Every atom, simultaneously, in 16 trillionths of a second. Molecules dissolve before the collapse even completes. The chemical bonds holding them together are electron-mediated. The instant the electron clouds begin moving, the bond geometries change. Molecules stop being molecules. Water stops being water. Proteins unfold. DNA disintegrates. Every biological process in the universe terminates in the same fraction of a second. The collapsing electrons hit the nuclei. At that point, the nuclei themselves are no longer stable in their usual sense. Protons and electrons combine through weak force interactions across the board. Protons become neutrons. Elements transmute. But this would not be controlled electron capture in specific unstable nuclei. It would be universal, simultaneous, catastrophic. The remaining neutrons would have no electron clouds to hold atoms at arm's length from each other. The Pauli exclusion principle still applies to the neutrons, but without the electron structure that keeps atoms separated in normal matter, the density of material would begin to approach neutron star densities. Everything compresses. In a neutron star, a teaspoon of material weighs as much as a mountain. That is what the entire Earth would approach, rapidly, catastrophically, in the absence of atomic structure. And then even that equilibrium might not hold. At sufficient densities, neutrons themselves break down into their constituent quarks. Matter as a recognizable thing ceases to exist. What remains is something like the conditions at the center of a collapsing stellar core. Unimaginably dense, unimaginably energetic, and completely unlike anything we call matter. The entire sequence, from normal matter to collapsed quarks, would happen in a time interval too short to have any name. The universe would not explode. It would implode. Every galaxy, every planet, every living thing, every structure of any kind, collapsing simultaneously toward nuclear density before any signal of the event could reach anything else. And all of that terror rests on one fact: the uncertainty principle does not turn off. The ground state holds. The electron's quantum pressure against confinement is real and consistent, and has never in the entire history of the observable universe failed to apply. The stability of matter is not guaranteed by the universe's indifference to alternatives. It is guaranteed by a specific set of physical laws that happen to produce quantum mechanics. Different laws would produce a different universe, almost certainly one without atoms, almost certainly one without anything. The electron's refusal to fall is the most consequential physical event that never happens. 16 trillion times per second, in every atom everywhere, the collapse that would end everything fails to occur. And the universe persists. But whether the laws that cause that failure are truly permanent, or whether there are conditions extreme enough to override them even briefly, is a question that physics has not finished answering. Everything in this story has pointed toward one conclusion: atomic stability holds. The ground state is real. The uncertainty principle is inviolable. The electron does not crash, but physics has a long history of rules that seemed inviolable until they were not. Newtonian gravity held for 200 years before Einstein showed it was an approximation. Maxwell's equations described light perfectly until quantum mechanics revealed that light also behaves as particles. Every framework in the history of physics has turned out to be incomplete in some regime. Every rule that seemed absolute eventually met a condition where it no longer fully applied. Quantum mechanics itself is known to be incomplete. It does not fully account for gravity. At the Planck scale, the smallest length that has physical meaning, distances roughly 1 trillion times smaller than an atomic nucleus, the known laws of physics break down entirely. Nobody knows what replaces them. The question of whether atomic stability holds under every conceivable condition in the universe is therefore genuinely open. The graphene experiment showed that there is a threshold linked to the fine structure constant, beyond which ordinary atomic physics fails, and a new regime appears. That threshold is real. Atoms near a supercharged nucleus behave differently. The vacuum itself becomes unstable. Particle pairs emerge. The electron's status as a bound, stable entity around the nucleus shifts. In the universe outside any laboratory, environments exist that push toward these extremes. At the surfaces of neutron stars, gravitational and magnetic fields reach strengths that would tear ordinary atoms apart instantly. The electrons that exist near neutron star surfaces are not in ordinary atomic ground states. They are in strongly magnetized, relativistically compressed states that have no analog in normal matter. Quantum mechanics still governs them, but the solutions look nothing like a hydrogen ground state. Near rotating black holes, space-time itself warps in ways that affect how quantum fields behave. The Unruh effect, confirmed through related physics, predicts that an accelerating observer sees a vacuum full of radiation that a stationary observer does not. The quantum vacuum, that seething sea of virtual particles out of which the atomic collapse regime can summon real electrons, is observer-dependent in a deep way. At the earliest moments of the universe, fractions of a second after the origin, temperatures and densities were so extreme that atoms could not exist at all. Electrons and nuclei could not bind. The universe was a plasma of free particles. Atomic structure only became possible once the universe cooled enough for quantum ground states to form. Whether there are conditions in the universe today, perhaps inside the cores of neutron stars, or in the intense fields near spinning black holes, or in regions where dark energy or unknown physics might operate, where the quantum ground state as we understand it fails, is an active area of research. The equations make predictions at the edges of those conditions, but those predictions have not been directly tested. The universe contains regions we have never and may never directly observe. What we know with certainty is this: in every atom on Earth, in every star, in every galaxy that has been observed, in every material ever measured, the quantum ground state holds. The electron stays where it belongs. the collapse never happens. What we suspect, based on everything we understand about how physics works at extremes, is that there are regimes where the rules stretch, shift, and eventually give way to something else. Something we have not fully described yet, something that may require the next generation of physics to explain. And somewhere in that unexplained regime, perhaps, is the final answer to the question we started with. How close can an electron get before the atom collapses? The answer for ordinary matter is clear and complete. The answer for the universe at its most extreme is still being written. The electron holds. For now, for here, for everything we can see. The rest remains open.